In thermochemistry and its allied field of thermodynamics, an important distinction is made between the system and the surroundings. Now, the system is whatever small part of the universe we are studying, and the surroundings is everything outside of that. And I think a natural picture image that comes to mind is that the system is sort of some enclosed region of space with a well-defined boundary. So something like this cow here. And then everything beyond the well-defined boundary would be the surroundings. And there certainly are chemical systems that are like this, that are a well-defined region of space with a definite boundary between them and the surroundings. But more often, you'll have a situation like the one in the chemical reaction between sodium hydroxide and hydrochloric acid in solution to form sodium chloride and water, where the reaction, the ions and the molecules in the reaction, they themselves are the system. So the sodium and hydroxide ion and the chloride and hydrogen ion would all be the system, and then the surroundings would be all of the water that those ions are dissolved in. And so here the system is not so much a region of space as it is a set of objects that we are interested in following. Now, when we're looking at thermochemical studies, we're looking at an exchange of heat between the system and the surroundings, and there are two fundamental ways that can happen. You can have heat flowing out of the system into the surroundings, and such a process is called an exothermic process, and it's called this because heat is flowing out of the system into the surroundings. The sign convention on this is that if heat is flowing out of the system is losing energy, and so the heat is given a negative sign. So the Q for an exothermic process is negative. And one important thing to be clear on is that when there's an exothermic process, heat is flowing out of the system and into the surroundings, and so the surroundings are getting warmer. And so if you've got a process where the surroundings are getting warmer, then that process is exothermic. The system itself is losing energy. Heat is flowing out of the system. And then, of course, the converse situation is where heat flows into the system from the surroundings. This is called an endothermic process. Endo means into, and so heat is flowing into the system in such a process. The system is gaining energy from this incoming heat, and so the sign convention is that Q, the heat, is as a positive sign. And since the heat is flowing from the surroundings get colder in an endothermic process. And so this is just something to keep in mind. When you are interested in measuring the magnitude of heat flowing into or out of a system, any apparatus that you would use for doing this measurement is called a calorimeter. And all calorimeters are fundamentally consist of some container with insulated walls. And you can have very fancy, sophisticated calorimeters. You can also have very simple calorimeters consisting of a styrofoam cup and a thermometer. And the important thing, the thing that makes both of these pieces of apparatus calorimeters, is that you've got an insulated container where you can put whatever it is that you're studying. And then you have a thermometer for keeping track of changes in temperature. And for precise work, for serious work, you would want to use a fancy calorimeter that has very thick, well-insulated walls. But for ordinary student work, it's very, very common to simply use an inexpensive insulated container like a styrofoam cup. One simple thing that you can do to improve the insulation on a cup calorimeter is just to put a second cup outside the first one, and that actually that improves the insulation quite a bit, and so that's a good thing to do. So I want to go through a couple examples of the kinds of studies or experiments that you might do with a calorimeter that you would use to measure the heat associated with a process. And the first example is we're going to be looking at a physical process where a hot object is the heat source for the calorimeter. And so the problem that I'm going to discuss is that a heated titanium cube having a mass of 73.7 grams is dropped into 215 milliliters of water at 21.2 degrees Celsius. The final temperature was 34.7 degrees Celsius. What was the initial temperature of the titanium cube? So the idea here is that we've got a calorimeter, some insulated container that contains 215 milliliters of water, and we've got a thermometer in there. The water has an initial temperature of 21.2 degrees Celsius, and then we drop in a hot cube of titanium, and the heat flows out of the hot titanium into the water. So the titanium cools off, the water heats up, and at the end of the process, both the titanium and the water are at a temperature of 34.7 degrees Celsius. And so the thing that we're trying to find out is what was the initial temperature of the titanium cube. So again, it's important to be clear on what it is that you're trying to find out when you're faced with a problem like this, and also it's important to understand the information that you're given. And so just for emphasis, the water is being heated from 21.2 degrees Celsius to 34.7 degrees Celsius. The temperature of the water is increasing, and then the titanium is cooling off. It's going from some high temperature down to 34.7 degrees Celsius. And so we're going to make an assumption that the calorimeter was perfectly insulated so that no heat escaped from the calorimeter. In other words, all of the heat that flowed out of the titanium just went into warming up the water. We're assuming that whatever amount of heat escaped from the whole calorimeter was small enough that we can ignore it. And so if under this assumption, whatever heat is coming into the water is the same as the heat that was leaving the titanium. The only thing that's different is that the heat was flowing out of the titanium, so that heat is negative, and the heat was flowing into the water, so that heat is positive. And so the two heats are equal and opposite in sign, and we can calculate the amount of heat based on the specific heat of the water and the titanium. So for each of these, for the water and for the titanium, the heat that is crossing into or out of the material is given by the specific heat of the substance times its mass in grams times the change in temperature. And we can look up the specific heat for water. That is 4.184 joules per gram degrees Celsius. For titanium, the specific heat is 0.72 joules per gram degrees Celsius. And then the mass of the titanium, that was given to us. That was 73.7 grams. The mass of the water, we weren't given that directly, but we were told that there was 215 milliliters of water. And so we can use the density. Water around room temperature has a density of about 1.00 grams per milliliter. So 215 milliliters will have a mass of 215 grams. So if we put in the heat capacity, the mass, and the change in temperature for the water and for the titanium, with a minus sign on the expression for titanium, set them equal to each other, that gives us this. And again, the temperature change is always the difference between the final and the initial temperature. So for the water, the final temperature was 34.7. The initial temperature was 21.2. When you subtract those, you find that the change in temperature was positive. The water heated up. For titanium, well, we don't know the initial temperature, but its temperature change was the final temperature, 34.7, minus whatever that initial temperature was. And so now this is kind of an ugly equation that I've got written here, but we can. The only unknown here is the initial temperature for the titanium, so we can just use algebra to solve this. And I'm not going to go through all the details, but if you divide through part of the stuff on the right, we get that this expression on the left is equal to 34.7 degrees Celsius minus the initial temperature. And then putting things into the calculator, we can find that the initial temperature of titanium was 264 degrees Celsius for this problem. Okay, so this is one example. This is an example where the heat source was a hot object, and so it was sort of a physical process of a hot object cooling off. The second example that I want to look at is a chemical process as a heat source. So using a chemical reaction to generate heat in a calorimeter. A chemical process, not really a reaction in this case. We're talking about dissolving sodium chloride in water. So a saturated solution of sodium chloride is prepared by dissolving 29.2 grams of NaCl in 100 milliliters of water. As the sodium chloride dissolved, the temperature of the solution fell from 22.3 degrees Celsius to 17.8 degrees Celsius. We want to determine the amount of heat that was involved in the dissolution process, assuming that the heat capacity of the solution is 3.30 joules per gram degrees Celsius. So here we've got our calorimeter that contains 100 milliliters of water, and then we're going to dump in 29.2 grams of sodium chloride and let the sodium chloride dissolve. And in the process, the temperature inside the calorimeter will drop. So the water and the sodium chloride the sodium chloride presumably was also at room temperature. I guess that's not said in the problem here, but we'll assume that the sodium chloride and the water are both sitting at room temperature at the beginning of the process, and then when you mix them together, the whole thing is cooling off down to 17.8 degrees Celsius. Okay, so let's be clear on what it is that we're trying to find. We want to find the amount of heat involved in the dissolution process. And thinking about the situation as it's described, the temperature of the solution dropped. So that tells us the heat flowed out of the water and into the sodium and chloride ions as they dissolved. So the water lost heat. The sodium and sodium chloride gained heat. So from the perspective of the sodium chloride that's dissolving, the process was endothermic. Heat flowed into the sodium chloride from the water. And so here, again, the heat associated with the system is equal and opposite to the heat for the surrounding water. And so the heat that was entering the sodium chloride is equal and opposite to the heat leaving the water. The heat entering the sodium chloride, well, that's what we're trying to find. So I'll just call that QNaCl. And then the heat leaving the solution, we can find that based on the temperature change. So we have the heat capacity of the solution times the mass of the solution in grams times the temperature change for the solution. The heat capacity of the solution that was given to us, that was 3.30 joules per gram degrees Celsius. The temperature change is going to be the difference between 17.8 degrees Celsius minus our initial temperature of 22.3 degrees Celsius. The mass of the solution we're going to find again from the volume of water using the density. So we had 100 grams of water, and then one thing that is really easy to forget, but is important, is that for this calculation, the heat that's leaving the solution, we need the total mass of the solution. And so that mass consists of the 29.2 grams of sodium chloride plus the 100 grams of water. And so the total mass of the solution is 129.2 grams. And then the temperature change is the final temperature, 17.8 degrees Celsius, minus the initial temperature of 22.3 degrees Celsius, and that works out to be negative 4.5 degrees Celsius, and that is to say the temperature dropped, so the temperature change was negative. So putting these quantities into our expression, the heat associated with the dissolution process is negative 3.30 joules per gram degree Celsius times 129.2 grams times negative 4.6 degrees Celsius. And then multiplying this out, we have two negatives. They multiply to give us a positive, and so the heat is positive 1,918.62 joules. And then for precision here, the precision is going to be limited by the precision, by the number of significant figures in the temperature change, which was 2, with the 4.5 degrees Celsius. So we'll round this off to 2 significant figures, and then I'm also just going to convert from joules to kilojoules, and so the final answer will be positive 1.9 kilojoules. And I'm writing the positive sign just to emphasize that this was an endothermic process, and so the heat associated with it was positive. Heat was flowing into the sodium chloride as it dissolved. Okay, and that is that for this video.